Welcome to all of you for the second lecture in the series of what is broadly called as modern physics. So in the last lecture, I gave you a broad outline of what I am going to discuss, and also gave you an equally broad outline of what you have supposed to have studied in mechanics, thermodynamics, and also in electricity and magnetism. The birth of modern physics, especially quantum physics, depends on all the three subjects. Some of the concepts were imported, as I told you, like for example, the principle of equipartition of energy, which we do not give up. But some of the concepts, we would have to reject them. Like for example, the concept of a trajectory is allowed in quantum mechanics, but it is not allowed in Bohr model of atom, for instance. So we took a broad overview of whatever we have learnt. Today what I wish to do is to start a discussion of photoelectric effect. But before that, it is good for us to actually ask what exactly is the evidence for wave nature of light. Now there are two aspects that are involved in discussion of the wave nature of light. One is to find general characteristics which are common to all kinds of waves. We have sound waves, we have water waves, we have waves propagating along, for example, a string when you shake it. All of them share some common properties. They are collective modes in some sense, and they all exhibit interference, diffraction, etc., etc. But then they all differ from each other. For example, sound waves in air are longitudinal vibrations. Waves in solids can be transverse or longitudinal. Deep sea waves are quite different from the surface waves. So they will all have different characteristics, and when we say we verify the wave nature, we should actually verify every single aspect of that particular wave, whatever wave we are considering, and then convince ourselves that we have indeed settled the matter. So when it comes to electromagnetic waves, Maxwell identified what we call as light to be nothing but a small part of the spectrum of electromagnetic waves. So if that be true, then we should be able to verify that light exhibits all electromagnetic properties as a wave. That is the important thing. So let us see how we can figure that out. The standard procedure is to look at the template, so to say, for all wave determination experiments, and that is the double slit interference. So what we have to do is to now look at the peculiarity of electromagnetic waves in the double slit experiment. At the end, at some time, actually I am going to go beyond double slit experiment, because the standard double slit experiment will not be able to show all the properties that we expect to verify. But let us start with a recall of the double slit experiment. So here is a schematic view which is based on the Huygens construction, and this is common to all waves. So you have the primary source S0, which you can see at the leftmost side. It emits waves. There are two slits S1 and S2. So these two slits act as secondary sources. Both the secondary sources are related to whatever the primary source is, therefore they are phase correlated. So each secondary source produces its own circular waves. The circular waves superpose on each other and they produce maxima and minima patterns. So they are showed, the superposition is showed there. Wherever there is a destructive interference, you have minima. Wherever there is constructive interference, you have maxima. So this is the overall picture of what happens in a double slit experiment. Now what we want to do is to go beyond this and see what exactly we want to verify in the case of light. So if we go back and look at interference, so let me go back. There are many important parameters that we have to pay attention to. One is the distance between the two slits S1 and S2. That is important for us. The next is the distance between the slits and the screen that you have put. along the perpendicular. That distance is also very important for us. And third, of course, what we need is the wavelength or the frequency of light. In general, the relation between the wave number and frequency can be wave number and frequency, or wave number and velocity can be quite complicated. But here we know what the relation is. So what we want to do is to treat all these parameters. But when it comes to light, not only do we worry about those three parameters, we also have to worry about the polarization of the two beams. This is very, very important. Remember, polarization was something that was known to Newton, and Newton was also the first person to observe the dispersion of light. So he took the prism, the light passed through it, and he was able to resolve all the 7 colors. And yet, in spite of what he had observed, he had very strong reasons to believe in the corpuscular theory of light. Although Huygens proposed the wave theory of light because of the enormous influence and the stature of Newton, people continued to believe in corpuscular theory of light. There were many, many different predictions made by the corpuscular theory and the wave theory. For example, according to the corpuscular theory, the speed of light in a medium should be greater than the speed of light in free space, what we call as vacuum. Of course, during Newton's time, there was no way to measure the speed of light. In fact, Newton performed a crude experiment by taking 2 lanterns which were separated maybe a few hundred meters, and one of them agreed to switch on the light, and the other person was supposed to record, and obviously it did not measure the speed of light. The speed of light was too enormous. So it was only Young's double slit experiment that actually decisively clinched the issue. So what we want to do is to add one more ingredient, namely the polarization. So because I am including the polarization, it is good for me to repeat the derivation of your double slit experiment, the phenomenon, in a slightly different fashion. I will not simply add amplitudes, I will actually add electric fields. So that is what we would like to do. So at this point, I will have to do a little bit of algebra and describe the experiment to you, and let me start with it. So let us recall what is happening in the case of electromagnetic wave, and then proceed to describe the experiment. Light. So in your study of electricity and magnetism, in the very last chapter, you people studied about the displacement current, Faraday's law of induction, Maxwell's equations in free space, and you observed that the parameter 1 over root mu naught epsilon naught has the dimension of speed. This is LT inverse, and numerically 1 over root mu naught epsilon naught is nothing but speed of light. This is numerical observation. Based on this observation, Maxwell speculated that what we call as light is nothing but an electromagnetic phenomenon. And if you people remember, there are 2 parameters that are sitting here. This is my permittivity. Free space permittivity, which corresponds to the electric field, and this is my permeability. This is my permeability. So the speed of light depends on what we can crudely call as the magnetic properties of the free space, which is characterized by mu naught, and the magnetic properties of electric properties of the free space, which we call as epsilon naught. So it is very tempting, and that is exactly what Maxwell did, and that is what led him to speculate and predict that what we call as light is nothing but a part of the electromagnetic spectrum. However, we should be careful in drawing such a conclusion, because in physics we proclaim, not often but always, that we introduce only those quantities that are measurable. If you look at your textbook carefully, what the textbook does is to say that mu naught is a definition. Nobody says that mu naught is defined, is measured. In fact, it is given as a definition, and then of course, once you give mu naught as a definition, you can always determine epsilon naught. This is not exactly a course on units and dimensions and what is measurable and what is not measurable, but I would invite all of you students to think a little bit about it and ponder over what is happening here. But for our purposes, we don't have to worry about that. What matters to us is the speed of light, and speed of light is an eminently measurable quantity because it is nothing but distance divided by the time taken by the signal. So that is something which is measurable, but please do think about it. But there is a lesson in this, even if I cannot measure mu naught and epsilon naught, namely my electromagnetic field is a complicated field in the sense that there are two amplitudes, the electric field, which is a function of time and space, and the magnetic field. What is the beauty of this? They do not need any external source, they act as sources for each other. So thanks to Faraday's law, which tells you that my magnetic field can actually give rise to an electric field. I can also put a spatial dependence. And again, if you make use of the concept of displacement current, which is nothing but the derivative of the electric field, it can actually give rise to magnetic field. They feed on each other, and that is the characteristic of the electromagnetic wave. There are two vector fields which act as sources for each other, therefore they are not independent of each other. So how do we then understand what their mutual dependence is? The way to do that is to observe that if you give me the frequency and the direction of propagation, so these are the two parameters, that is, it is a plane monochromatic wave, monochromatic plane wave, then everything is known if you give me the electric field. So I will write, for example, E equal to E naught cos k n dot r minus omega t. That is what I will write. So n is the direction of propagation, r is wherever the location is, t is your time, k is your wave number. So let me write expression for k, 2 pi by lambda, and omega is your angular frequency, which is nothing but 2 pi nu. And they satisfy the relation omega equal to kc. So the wisdom that we learn is, although that there are two vectors at every point in space which keep on varying in time, they are not independent of each other, because my magnetic field is nothing but the magnitude of the electric field divided by c, that is what I have, and the direction of the magnetic field is such that E cross B is parallel to n. So the direction fixes the direction of the magnetic field, the direction of propagation, because I have given the direction of the electric field, and the first relation fixes its magnitude. Of course, we should also remember that they are perpendicular to each other, and finally E dot n is also equal to 0. Meaning, if my wave is propagating in this particular direction, I am going to look at a plane which is perpendicular to that. If my electric field, for example, is in this direction, my magnetic field would be perpendicular to that. So let us say along this particular direction, B cross C equal to n, okay, along this particular direction, and the wave continues to propagate. Therefore, if I wish to verify the wave property of light and identify that with the light, I should also be able to factor in the polarization. So that is what we intend to do. So let us therefore repeat our analysis of the double slit experiment. So the double slit experiment is a fairly well understood, the geometry is well understood. So let me write the slit here. Since there are lines here, it is easy for me to, this is the slit. This is my source. So two light beams come here. So they will be coherent. So let me write the screen here, and I am going to look at a point, let us say somewhere here. This is my P, and the light ray that comes here is going to propagate at this particular point. This light is okay. This line is also going to come at this particular point. This is my midpoint. So this is the distance d. This is d by 2. This is d by 2. That is what I have. And this distance I will call as y. I will call this distance as y. Therefore, what I am going to do is to move my traveling microscope or any detector that I want along the y direction and see how the intensity varies as a function of y. So please notice what are all the parameters that I have here. These parameters are all standard. The distance between the two slits, S1 and S2 is d, and this is along the y-axis. That is what I have. And then the distance between these slits and the screen is capital D. This is along the x-axis. And then you have the two rays which are propagating. This direction is n1. This direction is n2. This figure is highly exaggerated in the sense that the distance between the two slits is quite comparable to the distance between the slits and the screen, and also the distance y. But in reality, that is not what is going to happen. Please remember that this capital D is much, much greater than small d. In fact, this is a very important thing for us because it is going to create some problems later when we try to verify. It is convenient to draw a line from the center of the two slits here, and I will call it as n. So this is the diagram. This is a common diagram to all waves. So what is it I want to do now? I want to write a polarization vector here and a polarization vector here. So what do I mean by polarization? By polarization I mean the direction of the electric field. It is a convention. The old German books, for example, were using magnetic field as the direction of polarization. The great book by Born at one point had magnetic field as the direction of polarization, but it doesn't matter because we know how to go from the electric field to the magnetic field. So I need a few more things for my analysis. So what I am going to do is to draw a line here, and I will call this angle beta, and I am going to draw a line here, and I am going to call this angle alpha. So this will be pi by 2 minus alpha. This will be pi by 2 minus beta. I need not write that. Now what I will do is to write down the expressions for the electric field and the magnetic field corresponding to this. So what do we have? Electric fields. So I will write E1 equal to E10 cos k n1 dot r minus omega t at any given point, and E2 is E20 cos k n2 dot r minus omega t. That is what we are going to write at any given point. So what will I do? I will resolve n1 and n2 along in the xy plane. Remember, I took the direction x to be when I move from the slits to the screen, and I took the direction y to be when I move along the screen. So please remember that, and I have defined angles alpha and beta with respect to the x axis. That is what I have to remember. So what are we going to write now? What we are going to write is to resolve and call this cos alpha I plus sin alpha j. I is the unit vector along the x direction, j is the unit vector along the y direction, and n2 is nothing but cos beta I plus sin beta j. That is what I have. So if I define the quantities in this particular manner, the difference between E1 and D2 would be known at any 2 points. Let us say this is evaluated at R1, this is evaluated at R2. By finding out the expressions for cos alpha, sin alpha, cos beta, sin beta, and that is what we are going to do. So how are we going to write that? We are going to look at this sheet again. So this is my angle beta. So cos beta will come from this, and cos beta will come from this. There is a distance d by 2 here, there is a distance minus d by 2 here if you feel like. So let me keep it at the side and let me write down the expression for cos alpha. So that is nothing but the adjacent side divided by the hypotenuse. That is what I have. So I will put my d here. So the hypotenuse is nothing but y minus d by 2 whole squared plus d squared, and I have to put a square root. So all that we have done is to make use of the Pythagoras theorem. So by the same token, my sin alpha will be what? It is nothing but the opposite side divided by the hypotenuse. So the opposite side is y minus d by 2, because I am measuring everything with respect to the center of the 2 slits. That is my origin. That is what I am writing. So I am going to divide it by that, and my denominator is of course the same, d squared plus d squared to the power of half. What happens in the case of cos beta sin beta? This y minus d by 2 will become y plus d by 2, because you have come further downwards, so you have increased the distance. That is what you are going to see. So this is at a distance d by 2, therefore it is y minus d by 2. This will be y plus d by 2. I am going to write that. But now if you people remember the approximation that I made, and what is the approximation? That I am going to ignore quantities small d by d. This is much less than 1. Sorry, this is not an approximation. This is the physical situation. Small d by capital D is very large. Small d may be of the order of a few millimeters, and capital D could be a few centimeters, tens of centimeters, or even more. Therefore, there is a large factor associated with them. Therefore, if you look at this y minus d by 2, y is also relatively small quantity. You cannot go to very large values of y, because intensity will start decreasing, your pattern will start becoming poorer. Therefore, you restrict to small values of y. So what happens is that this first term becomes quite small compared to capital D. So for all practical purposes, this is of the order 1. That is what we have, d by d plus some correction terms. So all of you are familiar with binomial expansion, so binomial corrections. Please work it out. Let me not waste your time here. However, when it comes to sin alpha, we want to keep the lowest order non-vanishing term. Again, the denominator is completely dominated by capital D, the distance between the slits and the screen. But in the numerator we have y, and y is of course larger than d because you are going to move it. Therefore, I will write it as y by d. That is what I am going to write. And interestingly, you should know this is exactly what you would get if you had computed the tan alpha also, y by d. So this approximation corresponds to writing sin alpha roughly equal to tan alpha. That is what your textbooks tell you. That is what you are going to do. But what is the beauty of this? The beauty of this is that I never made use of the fact that there is a y minus d by 2 that is sitting here. So for example, if I were to write down the expression for beta, this y minus d by 2 would go to y plus d by 2, and this would correspond to cos beta. And again, this would go to y plus d by 2, and this would correspond to sin beta. And in my approximation, whether you write y minus d by 2 or y plus d by 2, it does not matter. So I will get exactly the same expression. Therefore, your books tell you that we are discussing the two slit interference phenomenon in the parallel ray approximation. So that is the reason why I wrote this highly exaggerated picture. By no stretch of imagination are these two parallel. So what are we saying? We are saying that we can treat them as parallel. Where do two parallel lines meet? The two parallel lines will meet only at infinity. So for all practical purposes, this capital D is as good as infinity, which means to say that small d by d is very, very small, 10 to the power of minus 3, 10 to the power of minus 4, because in physics we never deal either with absolute 0 or absolute infinity. Infinity is not a number, 0 is not a measurable quantity, but this is the approximation that we are going to do. So if we did that, my n1 and n2 will become the same. Therefore, the only difference will be the magnitudes of the electric field at this point and this point. So that is all what I have to worry about, and I will start writing down the expression. So now I will write my expression. My E1 is nothing but E1 0 cos. Now I can write simply k dot r minus d by 2 minus omega t, and E2 will be E2 naught cos k dot r plus d by 2 minus omega t, where this r is measured here from the distance. I am doing a vectorial addition. That is all what I am doing. This is my r. So this is r1, this is r2, and this is my r. So that is what I have done, and this is our expression. In this experiment again, I have to go back to this diagram. There is a common source which is emitting radiation, and if the source is unpolarized, the two secondary sources will also be producing unpolarized beams, so to say unpolarized rays. And if the source is polarized, the polarization here and the polarization here will be the same. Therefore, this setup is not good enough for me to probe polarization effects. I have to do something more. I will come to that later. So at this point, I am mathematically keeping intact E1 naught and E2 naught, but you should appreciate that for our purpose, as far as this setup is concerned, E1 naught is parallel to E2 naught. There is no escaping that. So if we did that, my total electric field, my ET, is nothing but the superposition of E1 plus E2. E1 plus E2, and we know that energy depends on the total electric field, the magnitude of the total electric field at any given point, the energy density, And therefore, when I calculate the magnitude of the total electric field, not only do I add the squares of the magnitude of E1 and E2, I have to worry about their cross term. The energy density manifests as the intensity of the radiation that you see on the screen. Greater the energy density, greater the intensity, greater the amplitude, greater the energy. That is what we have to remember. Therefore, the pattern, whatever we are going to see, depends on whatever is in the cos, in the argument of the cos function, whereas the intensity depends on the magnitude of the electric field. That is something that we have to remember. They play a complementary role. So, if you remember that, my Et squared is nothing but mod E1 squared plus mod E2 squared plus twice E1 dot E2. This is what I have. So, one thing that we learn from this is that the minute you look at a radiation at a given time, whatever light is coming, not only do we have the addition of the two intensities, I always have an interference term. However, we demand coherence for the simple reason that we cannot take a instantaneous snapshot. That is something that we should always remember, because whether it is Young's double slit experiment or the experiments that you are going to do either in your 12th standard or in your higher classes, we deal with light in the visible spectrum where the frequencies of the order of 10 to the power of 14, 10 to the power of 15, let us say 10 to the power of 14. That means light wave is oscillating 10 to the power of 14 times per second, and our eye does not have that resolution. There is something called persistence of vision, which says that all images persist in our eyes for 1/20th of a second, that is 0.1. 10 to the power of minus 1 is an enormously large number compared to 10 to the power of minus 13 or 14. So, we do not have a photographic plate that is going to record, we are going to see an average picture. If the sources are incoherent, then of course what is going to happen is that all those images will be superposed and this will be washed out and you will have addition of intensities. Therefore, this is called incoherent addition of intensity. But if they are phase correlated, if they come from a common source, for example, they keep on matching each other, whatever may be happening in the primary source, you will continue to see this see the effects of this cross term, and we should be able to see the interference pattern. So, that is what we wish to do. So, that means that I have to average over the time period corresponding to so many oscillations, but then it is sufficient to average over one period. And everyone knows that cos squared average over one period will simply give you a factor of half. That is something that we always know. Therefore, my Et squared will be nothing but, so I will put an average sign here, half E1 squared plus half E2 squared, E1 squared, I am sorry, this is a wrong expression, Et squared half E1 0 squared plus half E2 0 squared plus, we will keep this E1 dot E2 average. Therefore, my task is to evaluate the time average of E1 dot E2, and we already have this expression. We are almost home. All that we need to do is to do a little bit of trigonometric exercise. So, evaluation of the cross term also called the interference term. So, this interference term can work either in favor or work at cross purposes. It can increase the intensity. In fact, it can make the intensity to 0. So this is one of the counterintuitive things where light plus light can give rise to darkness. That is what is happening. And maybe that was the reason why the great Newton was wary of imagining that light, when everyone wants to say give me light, he did not want that to be a phenomenon, a wave phenomenon. Of course, people had not seen the double slit experiment. So remember, my E1 is E1 0 cos k dot r minus d by 2 minus omega t. E2 is E2 naught cos k dot r plus d by 2 minus omega t. I want to take their dot product because I have already added them up and squared them. Therefore, I want to evaluate E1 dot E2. So what is this quantity? This is nothing but E1 0 dot E2 0. This is a term which you would not encounter with sound waves, for example. So this is the term that is going to be important for us, and I am going to write the expression for the two causes. If you assume that the polarizations are fixed in time, like plane polarization, you don't have to worry about that. So this time average will be nothing but the time average of the product of the two cos functions. So this cos function will come here, this argument will come here. I am not going to write that. Therefore, basically what I need is a formula for the product of the two cos functions. We will evaluate that and find the conditions for interference. Therefore, I have cos k dot r plus d by 2 minus omega t. It does not matter in which order I write, into cos k dot r minus d by 2 minus omega t. The two electric fields are different at the point P. We are evaluating at the point P. So now we make use of the expression that you people are all familiar with. Cos A cos B is half of cos A minus B plus cos A plus B. This will give me cos A cos B plus sin A sin B. This will give me cos A cos B minus sin A sin B. The 2 cancels, the 2 gives this. So what we want to write is LHS in terms of these forms. So I am going to get a factor of half. I am going to add the arguments and I am going to subtract the arguments. So if I first add the arguments, what am I going to get? I am going to get cos A plus B is going to give me k dot r minus omega t with a factor of 2. So that is what I am going to get. The k dot d by 2 will cancel minus k dot d by 2. So cos 2 k dot r minus omega t. That is what I am going to get. The next term is important for us. When I subtract the two terms, so this corresponds to this. When I subtract the two terms, k dot r minus omega t and the k dot r minus omega t, they cancel each other. That means all spatial dependence will go away. That is something that we have to remember. So I get the neat expression cos d by 2 plus d by 2 is d k dot d. this is what my expression is. I am supposed to calculate the time average of this, which is nothing but the time average of this. Now look at the first expression. It is oscillating with a frequency 2 pi by omega, period 2 pi by omega. When I average cos function over a period or a sine function over a period, it goes to 0. So this is going to 0. Therefore, I am left with the term half cos k dot d. That is what I am left with. So now at last we have an expression for the intensity for us, and what is it given by? The expression for the intensity is simply given by mod E1 squared plus mod E2 squared plus 2 E1 dot E2, and this we wrote as half E1 0 squared plus half E2 0 squared half cos k dot d. So where is the information on the point P that we were looking at? So let me come back to this picture. We are interested in the point P at a distance y from the y axis. That is what I have done. Where is the information on that? That information is here. You people can see. So if this term were not there, you would simply get a uniform intensity, E1 naught squared plus E2 naught squared. You are sending a monochromatic plane wave, that is what would happen. So what is this k dot d? Remember that the d or the distance vector is along the y axis. Therefore, this k dot d, you can, if you want, write alpha or beta, it really doesn't matter. This is nothing but kd. So let me call it as sin alpha or whatever you want to call it as. You could have even written sin beta, and this is nothing but kd, and sin alpha is roughly the same as tan alpha, and we got an expression for sin alpha, and that was nothing but y by d. I remember that. So please remember, y is the perpendicular distance, d is the horizontal distance, sin alpha is the same as tan alpha. Therefore, y divided by d is tan alpha. That is what we have, and this is my expression. Therefore, I have now got a final expression of the intensity as a function of y, which is given by the two constant terms half E1 0 squared plus half E2 0 squared. So we left out E1 0 dot E2 0, and presumably there is a factor of 2 because this was a 2 E1 dot E2. Therefore, I supply a factor of 2 here, 1 into 2. That is what we are going to supply, and now that is my full expression. So you have essentially E squared if they have the same intensity plus E1 dot E2, the intensity is the same but the angle can be different, into the cos k dot t term. So E1 0 dot E2 0, which multiplies cos k d y by d. This is the classic derivation which is made in wave theory, and what we have learnt here is not only to analyze interference experiment with some ordinary waves, we also know how to analyze and understand interference experiment with light waves, which can be called as vector waves. In fact, they are transverse, they are vector waves because they involve two fields, electric and magnetic fields. Now the rest of the analysis is very simple for you to do. All that you have to do is to find conditions for minima or maxima. I am not going to write that because it is really not required by us. So you demand that it will be a maxima whenever k dy by d is a integer multiple of 2 pi, because cos is a maximum at 0, 2 pi, so on and so forth. Cos is a minimum at pi, 3 pi, so on and so forth, because it takes the value minus 1. And cos, of course, is 0 when it is a multiple of pi by 2. That is what we have. So depending on how you, as you keep on changing your y, you are essentially keep on changing the value of your cos function. So depending on how we are going to move, we are going to get a maxima, which will be nothing but E1 0 squared plus E2 0 squared plus this quantity. So which will essentially that many times, twice the intensity. That is what we are going to find. Or if you are looking at the minima, this E10 dot E20 will exactly cancel the contribution coming from these two terms. That is the standard analysis. But all this will work if and only if my E10 is parallel to E20. Now what I can do is to play around with polarization. Play around with polarization. So E10 dot E20 is equal to E10 E20 magnitude parallel implies standard interference condition. Now suppose I perform the following experiment, and we will worry about how to do such an experiment. So I have a slit here, I am again exaggerating, and suppose two rays are coming here. Now what I will do is I will put a contraption which rotates your plane of polarization. I will put a contraption here. Or even better, let us say that unpolarized light is coming here, unpolarized. Now I will put a polarizer which will, let us say, polarizes my electric field in this direction, and here it will be cross polarized, and here my electric field will be in the opposite direction. Suppose I did that. Now the two polarizations are not parallel, they are in fact anti-parallel. So what will happen to the cross product term now? E10 dot E20 will become minus E10 E20 magnitude. Now that means what is happening is, instead of getting a plus term, I am getting a minus term. So where will the intensity maxima appear? Intensity will be maximum, a maximum if cos, that argument is minus 1, because this minus 1 will cancel this minus 1. It is just the opposite. So if I did this, then I know that I am looking at a phenomenon which is coming from light. So all of you might have heard of the discovery of this particle called Hicks, the God particle. So if you go and ask a serious experimentalist, the experimentalist tell you that, look here, I have seen a Hicks, I do not know if I have seen the Hicks. You have to study every single property to convince yourself that it is indeed the phenomenon. It is quite true that when you see the interference pattern coming from the Young double slit experiment, it could be nothing other than that of light. But it is still a matter of faith, and it is not a matter of complete demonstration. That is what physics has taught us repeatedly. And many times, because we make that assumption, there are many pitfalls in which we get trapped. Now suppose we start playing around. So what I will do is, I will look at this double slit again. I will start with a source here which produces unpolarized light, and I will put two polarizers through which my light rays will propagate and they will fall on the screen, and these two polarizers can be rotated independently, aligned independently. So they can produce polarization in the same direction. So E1 0 parallel to E2 0, or they can make E1 0 anti-parallel to E1 0. So E1 0 is minus E2 0. I am writing the unit vector to emphasize the direction. Anyway, since they are coming from the same source, slit width will be the same, the intensity will be the same, the magnitude will be the same. Or the third option, for example, is E1 0 dot E2 0 is identically equal to 0. They are perpendicular. So if this is the propagation direction, one of them will be in one direction perpendicular in the plane that is perpendicular, whereas the other electric field will be in the exactly opposite direction but in the same plane. Now you see the conclusions that we draw on the interference pattern will change. Interference conditions get modified. So E1 0 parallel to E2 0, standard conditions. What are the standard conditions? Maxima at even multiples of 2 pi, minima at mod multiples of 2 pi. If E1 0 anti-parallel to E2 naught, exactly opposite conditions. Now the conditions for the maxima and the minima will change. That is what is going to happen. And of course, if E1 0 perpendicular to E2 0, the pattern vanishes completely. So in other words, study of the standard double slit interference experiment, which is almost beaten to death, actually gives us an opportunity to explore additional properties of light, and this is required. Please remember, each one of these statements is going to acquire a different meaning when we do photoelectric effect or the Bohr model. Therefore, it is very important for us to pay attention to these things. Therefore, what should you do? You should go to your classroom, ask your teacher to please perform an experiment and demonstrate to you that actually this can be done. Or if you cannot do that, go to a nearby college, come to IIT and ask them to do that, and you will see that it is not such an easy thing. Why is that so? Because it goes back to the fact that this distance d is small, fraction of a centimeter, and it is not going to be an easy task for you to put a polarizer or an analyzer. So that may be one of the reasons why these experiments were not done in the double slit configuration. But if you think a little bit and go back and see what is it that caused interference, it is not so very much the double slit as the fact that there is a phase difference. This phase difference is produced by what? The path difference. So if you can somehow produce a path difference which does not depend on the two slits, then we have done our job. Smart experimentalists have actually produced such interferometers where things can be controlled very well. One of them is very, very famous, Michelson interferometer. So this great experimentalist was actually able to measure the speed of light with enormous accuracy. And not only that, he undertook the mission to measure the speed of the earth with respect to ether. So that was a great, great experiment which was a null result. And there is a modification of that which is called Maxender Interferometer, where what you essentially do is to manipulate the system in such a way that D is large. The arms are far, far away so that you can actually put a polarizer. So that is what we want to show here. This is a Maxender polarizer. So you see you have a system of prisms. So there is a light beam that comes here, there is a beam splitter, half of it goes here, half of it goes there, it gets reflected and you see the reflected pattern. Because they have traversed two different paths, there is going to be a path difference. Because there is a path difference, there is going to be a phase difference, and that is what you are going to look at, cos squared delta phi by 2, sin squared delta phi by 2. So you put your detector and you will, when you superpose these two waves, this wave coming here and the wave coming here, and what you do in order to create a path difference is to make it go through a medium or change the arm length. One of the two things, that is what you are going to do, and you ask for the interference pattern. Now this is a much larger system, and therefore now you can put your analyzer, you can put your polarizer, and you should be able to verify whether whatever we have predicted in this sheet of paper, namely parallel is standard condition, anti-parallel is opposite condition, and the interference pattern vanishes exactly. So this is something that has been verified only very, very recently, and here are the results. The interference pattern that is produced here is quite complicated, and it is beyond our scope to discuss that. So all that I can ask you is to look at them carefully and see that there is a difference in the interference pattern. This is the normal configuration when the two are parallel to each other. You see those fringes that are superposed over each other, circular fringes. Now when it make it 45 degrees, you get beautiful straight lines. That is what you are going to do. And then when I make it 90 degrees, you see it is almost completely different. The pattern is completely different. And minus 45 degrees is again going to produce the straight lines. So although in this experiment I have not been able to correlate exactly what is happening between the polarizer analyzer system and the equations that I wrote, because the patterns are different, you can at least see that there is a sensitivity to the dot product term E1 dot E2. So what is the lesson that we have learned? This is a paper that has been published in American Journal of Physics. There will hopefully be a supplementary material where we will provide you with all the references. There is no reason to clutter up our lecture with those things. We will certainly do that. That means we can be secure in our belief, in our understanding that the wave theory of electromagnetic radiation, and in particular light, rests on very, very solid foundations. Reflection, refraction, total internal reflection, diffraction, interference, every one of these phenomena, and interference depending on the polarization, surely points out that light can be understood in no way other than what? As a wave. But still we are going to encounter experiments which tell us no, that is not the truth, there is something beyond that, and that is the reason why I spent a considerable time explaining the well known things. Now what we shall do is to go beyond what is well known. So let us start with the experiments. So the conclusion has already been stated, but let me repeat. We can alter conditions on minima and maxima. energy is proportional to E squared. That is the next condition, because as you keep on varying the intensity or the amplitude, the intensity on of the fringes also changes. The condition for maxima and minima will not change, but how intense will be the brightest, that will certainly depend on the value of E squared. Therefore, wave theory of light rests on secure experimental foundations. So now we come to photoelectric effect, and it is good to give a certain timeline of what kind of developments took place in the experiments. This timeline has actually been picked up by me from your 12th standard book. Let me read that, leave you today, so that from the next lecture onwards I can actually start discussing the experiment and Einstein's explanation. So 1887 was the year when Hertz discovered photoelectric emission. Maxwell's equations were just being written around that time. And in 1897, J.J. Thomson discovered the electron, and he put a capacitor plate, saw the deflection and concluded that they are negatively charged. Hertz's experiment was not very refined or conclusive, but between 1888 and 1902, Hallenbach and Lenard performed a series of experiments. That is where they saw that famous linear behavior between the stopping potential and the frequency, which you are going to study, which I have already studied. And then came 1905. 1905 is known as Annus Mirabilis, the miraculous year, because Einstein wrote 3 great papers. Photoelectric paper is one of them. So Einstein gave his theory in terms of the photons, and in 1915 Millikan repeated this experiment with enormous accuracy and actually determined the Planck's constant in an independent fashion. So I am going to stop at this particular point, but I would like to repeat a statement of what Millikan said. In 1915, Millikan said that in spite of the great agreement between the theory of Mr. Einstein and what we have seen experimentally, it is impossible to believe in photoelectric effect, because that cannot be a theory and it is against all our understanding. And in 1951, all that you have to do is to invert 1.5 to 5.1. The same great man said that we have no option but to believe in photoelectric effect and quantum mechanics. The rest of the world had moved on. Great developments took place between 1920 and 1950, but Robert Millikan took 45 years to accept Einstein's explanation. And we will continue.